Okay, so this is going to be the senior project final report for my AI algorithms for single digit classification. So for the final report, we're going to start with the logistic regression that I have because I ran it because this one takes a while to run and I already have it ran. So to start out, these are just the libraries that I needed to import for all the commands. And next is I'm making a backend cluster here and registering the parallel, and that's for down here when we're learning, when the machine's learning, so that way I can use parallel true. And then the next part is setting up all the variables to be able to learn with. So these are pretty much the same variables as the neural network algorithm, which you can just use for the logistic regression because it doesn't really matter that much. It's just how it learns is the different way down here. But the train labels are, it's just like a big list of, or in the train images, a big list, 60,000 28 by 28 images with their pixels. Um, in the images of that and the labels are like 0 to 9, and it's associated with each one. So I can actually print both for you and just show you. Uh, View trained images. It's kind of obnoxious to look at, but this is each pixel. 0 means white, and it measures the color of the pixel, and anything that's not 0 is grayer all the way to black, and black would be 255. In the train labels, a lot easier to look at. It is, oh, this is actually after it's already been run, but the 6 here, there's a 1 here, that means there was actually 1, the first one was a 5, but because our index is from 1, it's assigning it here as a 6. And it's doing the same thing with the test images and test labels. And here is why it makes it look like this, and actually why this looks like this as well. Here we're reshaping the arrays to be how the learning line down here to train the machine, how it's expecting it to be. That's pretty much what that's doing. And then here we're changing both labels to categorical of the label. We're resetting it to like itself from just 0 to 9, and that's what becomes this. And here's the actual learning line of code. And I have it in a try catch here because sometimes there is a warning that pops up that stops it from executing the next lines of code for some reason, even though it's just a warning. So, and before you had to press like the little stop button that would be here to make it continue. So I put the try catch, so if it catches a warning, it'll continue. But here, we're using trained images, which is this whole big thing, 60,000 of them. This is just one. And we're associating it with the train labels to be able to associate the label with the image in multinomial, because we're doing multiple, not just 2, we're doing 10. And then multinomial is grouped. And then we're using the parallel. And this is just a summary and printing of it. I should show you that. And here we did get the warning. This is also a problem with the warning sometimes. It could actually just straight up not assign something to test data final, which I still haven't figured out a fix to, or why it's even doing this. Because this program did work before, but I didn't change anything, and now it doesn't, and I haven't been able to find a fix in time. But this did work at one point. But since it can't assign, it's not assigning anything to test data final, it's not going to be able to do the prediction here, which is right here, because there's no test data final. But this would have gone through. This will go through. It's using the test data final. It's using that to predict the test images, which would just be the like how it is all the way down here. Just test ones, just different ones. And then I'm just printing it here. What the prediction would be. And then the stop cluster here just stops the cluster because we started it up top, and you need to stop it because it doesn't stop at its own or on its own. And next, I have so you can input your own image to test it, which we also won't be able to test because there's no test data final currently, but because it didn't assign one, but I can still explain it. So I'm making an array here where I am assigning my own, not assigning my own, making my own array of 28 by 28 by 1, which is the same thing as the dataset, which is just 28 by 28 by 60,000. It's the same thing. Here just counts I need for my for loop to be able to map each pixel of the image, which is done here. This is the image I'm inputting, which I could probably just call plot image. It'll show up over here. It's probably still here actually. Oh no, that's the wrong one. This is the image that's being plotted. And for the for loop, I'm going through each pixel in the picture and then plotting it in this array with color at in the value. And color at gives a 0 for white and a 1 for black, and everything in between is in between 0 and 1. And that's what I'm doing here, which this is just the array before anything happens. And this is what it'll look like when the for loop goes through. See how it's kind of like the for over here. And within the for loop, this is the color at. This is where I'm setting into the array the color of the pixel. And here, actually, from what I looked up with color at, 0 is supposed to be white and 1's supposed to be black, but that wasn't the case. So I'm just flipping the 1s and 0s here. That's all that does. Here I am multiplying the number by 254 because in the test images and the trained images, when you actually look at them here after they, just like what they're in there, see I have 254s here. This is what they look like in the train and test images as well. But I've never seen a 255 in there. So back when you go to divide it, like up here, it divides it back down. But I've never actually seen a 255 in any of those, so I put it up to 254 on my own. In here, we're just reshaping the array back to the size, like we do up here. And then you just predict the image with the test data final, which would be something normally. And then the new array, which is this. And then you just print it. Yeah, and that's pretty much it for the logistic regression. So now we can go on to the neural network, which this one's a lot shorter, so I'll run it mid-video here. Or it takes a lot shorter time to learn. So up top here is just the libraries you're going to need. Here's just importing the MNIST dataset. This is basically like the logistic regression one. The trained images, they're the same thing. You just import them from the MNIST dataset. I'm just printing them here. It's irrelevant to see what they were. This is the neural network here, and we have 2 layers here. The first layer having the input shape of 28 by 28, which is the size of the images. The second layer here having the 10 units, assumingly for 0 to 9. And activation is softmax, which is normally used in classification, which is what this program is doing for 0 to 9. Here we have a compiler for optimization, loss, and measuring accuracy. Optimizer for RMS propagation for or root mean square propagation for going back and optimizing itself through each time. Loss categorical cross entropy, looking at the loss of which ones were wrong. Same with the accuracy, is actually putting out the accuracy in a percentage. In here is just reshaping for like how the network expects. With the 255, like how it would be here, it's the same. Same with the two categorical 0 to 9. That's it. And then this one, this is how the neural network learns, where we fit with the trained images and the trained labels. And it's going to run through them all 5 times here with increasing accuracy. And we'll just run that now. As here, this is the first time it's running through. And the accuracy is right here. Oh, on this side right here. The first run through had 94%. Second run about 97, and so on. And we can wait for it to finish. And now we have about a 99% accuracy here with this learning. You can change the epoch to whatever, to like 10, 20, but the more you have, I was getting some overfitting, so the accuracy would go down. I did it up to 10. 10 didn't seem like there was too much overfitting. You can probably do around that, but 5 was a pretty decent one. In here, we're just evaluating the accuracy with the test images, not with the trained stuff. So the trained one's always going to be lower, the accuracy, because it's not what it trained with. So we'll run that and see what it gives us. Yeah, and the accuracy is about 97.5% compared to 99%. It's not that much lower, but still noticeable. And this line is just predicting the first 20 images in the test images, which you can run that as well. So the test image is 72104, that's what it thinks it is. We can actually check that. Oh, that was the wrong one to test. That was the wrong one to print. We want to do the test labels to see if it's the same. Let me just do this again. Then we can do the test labels to see what they are. As you can see, the first one's 7. It's 8 here, but in reality it's this, but the indexing. So it's 8. 2, which would be a 3 here. And then 1, 0. And then 4, which is 5. So it's predicting them correctly. Just okay. Now this part is me inputting my own image to predict. This one we can actually run because we didn't have the problem like the other one. So it's actually the same thing as the one with the logistic regression, except the prediction line of code down here is just different. That's like the only difference. So we can just run this with, I guess I'll do it 2. I made a bunch of images on my own that are all, and the images have to be 28 by 28 pixels or else this won't work. It won't know how to like evaluate it either. We can just wait for this. And the image should show up over here. Oh, I gotta press play. Okay, so this was the image. It does think it's a 2 here. And then this is what my for loop made it look like. The 254s are like the black. So, looks like a 2 there. Okay. And this is actually new to what I've done. I have made a GUI for both of them, but we can't test the logistic regression one because it still has the problem, and it takes a long time to learn. I actually forgot to say that about the logistic regression. Even when it was working, it was probably taking around like 30 to 40 minutes to learn the way I had it learning. So I don't have this one, but the GUI is the same for both of them. It's just the learning code's different. It's the same thing. So here in the GUI, I'll explain the code before we run it. The window, G window, this is the main, like the whole window of the program. And I just named it neural network tester, that's it. And then the group main is where all of the objects below, like the labels and buttons, are going to be put into. And it's just group main. And I have horizontals false, so they don't pack side by side, they pack top to bottom when you add a new one. It's just button train. I have this just to train the network. It's the first button you're going to see. All these go in order, so you really can't mess up this GUI. It'd be pretty hard. And then I just have a loading label that shows up, and then it gets into the learning. This is for the neural network tester. It gets into the learning. It's literally the same thing as I have here for when it learns. I just put it here for it to do it in the GUI, and then I just have a finished loading label show up when it's done. And then I have a text box show up that says to oh, we're frozen here. Okay. I have a text box show up that says type the image path here. Right now you have to type the image path to where the image is on your computer. And you have to use double backslashes here because R uses a first backslash as an escape character. And then all these are in the group main. That's why you're seeing a bunch of group mains here. It's just all there. These are the buttons. And function is just, this is like the handler, what happens when you press the button. That's on all the buttons. I just have them doing different stuff. This is an important one because this is where I'm inputting my own image. This is a predict the image button. Once you have something typed up here, you press this, and then this right here is getting the image path from the text field and putting it into a variable. And this right here, image chosen, is actually printing the image onto the GUI so you can see the image you picked. And this whole part right here is just the predict neural network part here, my own. It's the same thing as this. I just put it in the GUI. And then these are just me concatenating strings to print out what the computer guessed. What the number would be. And we can run this one. So here, we train the network. It shows up, please wait. And I'll drag this up when I can. Oh. As you see right here, it's just learning, like before. We just need to wait for it to be done. Now I'm just gonna grab a path because I'm lazy. You just type it in here, and you do predict the image. It's gonna show up like the 2. It's the same one we had before the 2, and the machine guesses it's the 2. You can type a bunch of others in, and it'll show up right below it. Let's do the 5. That's the 5 I drew, and it thinks it's a 3. You could just keep going with the same one, or just like it'll extend the window on its own as well. You can do 6. So that's pretty much it. That's what I have. And like I said, the logistic regression tester, it's exactly the same as the neural network one I just showed. It's just the learning or the predicting here is just the prediction from the logistic regression one, and it's the same with the learning here. It's the same as the logistic regression. I just put it in the GUI. So that's pretty much it. Thanks.